LAMMPS and work on the COCOS package in LAMMPS, which runs on GPUs and multi-core CPUs. Previously, I worked on the long-range electrostatics method in LAMMPS, and I have engineering, and my dissertation focused on MD as well. Okay, so here's just a little bit of background on molecular dynamics. So molecular dynamics is trying to model atom behavior using Newton's law of motion. And you may have heard of quantum chemistry or density functional theory. So molecular dynamics isn't modeling the electrons. We are using an empirical expression for forces typically. And if we have this expression, we can take the atom positions, calculate the force of the velocities, and then calculate the new positions of the atoms and time step through time and evolve the atom positions over time. And so through molecular dynamics, we can model materials, biological systems. We can look at the behavior of atom and molecules. And one key difference between molecular dynamics versus, say, density functional theory is that we use a spherical cutoff, and this gives us linear scaling, and so we can simulate billions of atoms on a supercomputer, whereas with density functional theory, we're limited to, say maybe 1,000 would be a state-of-the-art calculation, 1,000 atoms on a supercomputer. Okay, so this is just a simple example. So in this example, we have a simple circle with called Leonard Jones, and the atoms in the blue and the green are fixed, so they don't move, and then the atoms in the red have this force model. And as you can see, as we pull apart the green and the blue, the atoms crack. So this is a really, really simple kind of toy example, but you can see that, if we had a supercomputer, we could scale this to billions of, or at least millions of atoms and look at material behavior, say, of an alloy using a realistic model. Okay, so how does it work? How does LAMMPS parallelize the calculation? Well, in molecular dynamics, we typically, or at least in LAMMPS, we have a domain decomposition. So each different processor will have own part of the subdomain. Typically use a cuboid, like a rectangular simulation box. Let me go to the next slide. And in order to calculate the forces on the atoms, we need to have what's called a halo exchange region or a ghost region. And so we extend the processor domain so that there's some overlap in between the different subdomains of the processors. And then we communicate information between the subdomains. And this typically point to point. So just the nearest neighbor MPI communication. Okay, so I want to also talk a little bit about neighbor lists. So in molecular dynamics, we typically have a neighbor list, which is just a list of all of the atoms inside a spherical cutoff around a central atom. And typically we'll include the cutoff plus a little bit of extra, which is called the neighbor skin. And that way we don't have to rebuild the neighbor list every time step. So if we have a little bit of extra, we know, on average how fast the atoms are moving, and we can know how big to make that skin size so that we only have to rebuild the neighbor list, say, every 20 time steps or so, 10 to 20, somewhere around there. There's another option in LAMMPS. So because of Newton's laws of motion, the force on one atom in a pairwise sense is the equal and opposite force on the other atom. So if you have two atoms interacting, they have a force. You can relate the force on one to the other through Newton's third law of motion. So there's an option. Either you can have only one. So if the atoms are inside this ghost region, you can have one processor calculate the interaction and update both the central and the neighbor atom, or you can have both processors do the redundant computation, and then you don't have to communicate this data. So this in LAMMPS is called the Newton flag. And so if you set it to on, then you save computation, but then you have to do more communication. And whether or not this is faster depends on, a few different things like the problem size, how long your cutoff is, if you're on a GPU or a CPU. It's normally better to have Newton off for GPUs. I'm just going to pause here and say, if anybody has any questions, please feel free to interrupt. I want this to be interactive. I have about 40 slides, but if you have specific questions or something doesn't make sense, please speak up.
I will add that we can also use the chat box, and then something you can check that as well if you feel comfortable.
Yeah, and if you could help me, if there's a question, pause me, because I might not catch it right away in the chat.
Sure.
Okay, so yeah, so with the neighbor list, there are also a few different options as well. So for CPUs, we typically use what's called a half neighbor list. And so in order to avoid doing redundant computation, each atom pair is only stored once in the neighbor list. And so that way the calculation for each pair is only computed once. And so this is typically better for CPUs. But if you're on a GPU or if you're trying to use multi-threading, then it requires atomic operations for thread safety. You have a write conflict for the forces when you update the forces on the different atoms. So another option is to use what's called a full neighbor list. So this basically doubles the computation, but reduces the communication. It doesn't require atomic operations for thread safety. And so even though it's twice as much work for a pairwise potential, it can still be faster on GPUs because you don't have to use atomics. Okay, so we talked about the main decomposition. We've talked about the neighbor list. Now we want to talk a little bit about molecular topology. So in one of the benchmarks that we'll talk about in a minute, one of the tasks that we have, it includes bonds, angles, dihedrals, and impropers. And so I just wanted to give a brief background of what this means. So a bond is basically a constraint. So it's a length between two atoms. Angle is, as you would expect, a constrained angle between three atoms. But then there's also constraints between four atoms, two different types. One is called a dihedral, and one's called an improper. So in the Rhodopsin benchmark, which is one of the tasks, it has all of these different constraints to hold the molecule's position in space. One other thing that we use in LAMMPS to speed up the simulation when we have angles and bonds is what's called the shake algorithm. So it's basically, if you think you have a water molecule and you have two bonds between the three different atoms. If you try to simulate that in LAMMPS without any constraints, you'll get a really high frequency wiggle of the bonds. And in order to capture that, you need a really small time step, which slows down your simulation. And so we can just say we don't really care about that really high frequency wiggle in the bonds, and we can just fix numerically the bond length and the angle. That's what fix shake does. And because of that, we can use a much longer time step because we don't have to simulate that high frequency oscillation in the bond. And that's called fix shake in LAMMPS. One other thing in this Rhodopsin benchmark is that in order to simulate charged interactions. So if you have a positive or negative charge on the molecule, the long-range coulomics are simulated in LAMMPS. So the Coulomb interaction is very long range, it's 1/r, and typically just truncating it with a spherical cutoff like we talked about is not a good model. It doesn't capture the physics. And so we need some way to simulate much, much larger than cutoff, many periodic dimensions of the box. And so we use what's called a KSpace method in LAMMPS. And the particle mesh, or P3M, PPPM method, is usually the fastest. That's what's in the Rhodopsin benchmark. It uses a fast Fourier transform. And so by including this KSpace method, we can simulate the long-range behavior of this charge interaction. Typically, we'll specify a relative accuracy. So, 1 × 4 accuracy in the forces. And in LAMMPS, it's called a long, so coulomic long peristyle instead of a cut. And so if you use a long peristyle, that means that you're using this long range electrostatics. And one neat thing about this method is that you can vary the Coulomb cutoff. So we typically set something like 10 angstroms for the cutoff, but because you can shift the work between the short range and the long range part, you can vary the cutoff, and LAMMPS will try to maintain the same relative accuracy, so 1 × 4. And so that's one parameter that we can tune. You might, on a GPU, you might want to have a longer cutoff to have more work in the short range part and less on the long range part. So that's one parameter we can tune. Okay, so we talked about, different parts of the calculation. So I just wanted to review kind of a basic MD time step. So this is during each time step without a neighborless build. We do an initial integrate, so that's relating the forces to the velocities and the positions of the atoms. We do some MPI communication, so that's the ghost region or the halo exchange, where we have to communicate inside the overlap region. And then we're going to compute the forces. So that includes the peristyle, that's the pairwise interaction, bonds, the molecular topology that we talked about, as well as the long-range electrostatics in the KSpace style. Additional MPI communication if we use this Newton flag, and then we do a final integrate. So we use a Verla similar to the leapfrog algorithm to integrate the atom positions and time. And then we do output. So, LAMMPS also is very modular. You can do a lot of diagnostics. You can have thermodynamic output. And so, that's another thing that I haven't captured here, but that can be scattered throughout the time step. Okay, so here's just a basic introduction to the different files in LAMMPS. So, and kind of the terminology of LAMMPS. So we have the input file, which is basically the list of commands that you're going to run in the simulation. So this says, this defines the model. It says how many time steps to run for, and just basically all the parameters of the simulation. Then we have a log file. A log file is a text file that has thermodynamic output, energy, pressure. It also has timing data. So how long did it take to run your simulation, a timing breakdown, where was the time spent in the simulation. And then we can also have other files. One is a dump file, so that's a snapshot of atom properties. So if we want to know all the forces, we can dump that out to a text file. If we want to do a binary checkpoint file, then that's called a restart file in LAMMPS. And then there's also a data file. And so in the Rhodopsin benchmark, we have what's called a data file that basically has all the initial positions of the atoms and of the molecules, the topology basically says, you know, what is the starting configuration of the simulation. Okay, so now that we have a little bit of background on LAMMPS, how do we get LAMMPS? How do we run it? How do we compile it? So this is a slide on downloading LAMMPS. So there's a few different options. You can go to GitHub and grab the latest release as a zip file or a tarball. You can also clone through git clone. So I'm not going to go over, you know, all the git commands, but you can clone the master version of LAMMPS and then use git. You can also go to the LAMMPS website and just download a gzip tar file. There's a few different flavors of LAMMPS releases. One is called a stable release, which is, you know, has more testing. It's more stable as the, you know, as the name implies. And then there's also what we call patches, which are, you know, periodic, maybe every month or so we'll release a new patch in LAMMPS. And then there's also, if you follow like the master version of the Git repository, that's, you know, every day there are commits added to LAMMPS. So that would be the least stable. You know, there might be a bug introduced that we'll fix tomorrow. So, you know, for the purposes of this work, I'd probably recommend a stable version unless there's some feature in LAMMPS that you need, and then you could use a different patch. Okay, so we talked about downloading LAMMPS. Now we're going to talk about compiling LAMMPS. So LAMMPS supports both a makefile, what we call the traditional GNU make system, as well as a CMake interface. And you know, you can use either one, whichever one you're more comfortable with. If you go to this lamps.sandia.gov website, there are instructions on building LAMMPS for both CPU and GPU. So, you know, at the very least, you need a C++ compiler. The LAMMPS requires C++11 standard. You need a API library, or you can also use the stubs library with LAMMPS. It's basically a dummy interface to MPI. And so I'm not going to fully cover how to compile LAMMPS because, you know, it's system dependent. But you can go to this website and see the instructions. Okay, so that's compiling LAMMPS. Now, how do you run LAMMPS? Well, so, you know, as I said before, there's all of these instructions are on the LAMMPS website. It's a great resource to look at. But basically, in serial, you're going to call the LAMMPS executable, and then you need to specify the input script. And the way that we specify that is with the -in flag. And so in parallel, you'd have like an run command, the LAMMPS executable -in, like the in flag, and then the name of the input script, which we are going to give you as part of the benchmarks. So for example, the Leonard Jones benchmark is in.lj, and the Rhodopsin benchmark is in.roto. And so this is a very basic run command. You know, to get reasonable performance, you probably need to set some sort of affinity and have, you know, different options in LAMMPS that we'll talk about more in a moment. And again, there's more command line options that you can use to tune your simulation that are described in the LAMMPS documentation. Okay, so we talked about downloading LAMMPS. We talked about just basic compiling and running. Now I want to focus on the what we call the accelerator, or actually the optional packages. So LAMMPS is very modular, and we don't include all the source code in you know, a default build. And so there are optional packages that you need to install to get optional features. And so to run the Leonard Jones benchmark, it's so basic that you don't need to install any additional packages. But the Rhodopsin benchmark, because it has fixed shake, long range electrostatics, and molecular topology, you actually need to install 3 optional packages: the molecule package, the KSpace package, and the rigid package. And the way that you do that in LAMMPS depends on whether you're using the traditional makefile-based system or CMake. So with traditional make, you just say make yes molecule, make yes KSpace, make yes rigid. That will install these optional packages, and then you'll build LAMMPS.
Ok, se van a llevar las sillas, sí. Mira, allá hay otra detrás del archivero. Con cuidado. No, alguien adelante y alguien atrás porque va. Ok. Sorry about that.
Okay, sorry, did you have a question or?
No, I failed to mute my microphone, sorry.
Okay, no worries. Okay, if it's with CMake, then you have this -D package molecule, yes, and you do the same for KSpace and rigid. And so in order to run Rhodopsin benchmark, like I said before, you have to install these 3 optional packages. Otherwise, you cannot compile. Well, you can compile LAMMPS, but it won't run the benchmark. It'll say, you know, I can't find the commands that you're requesting. Okay, so those are some optional packages. There are other optional packages that we call accelerator packages. So some hardware like GPUs or multi-threaded CPUs require special code. So for example, CUDA for GPUs, NVIDIA GPUs, to fully take advantage of the hardware. And in LAMMPS, these are implemented as what we call accelerator packages. So these are really similar to the other optional packages, except that they enable us to run LAMMPS on different hardware. So LAMMPS has 5 accelerator packages, and I'll go through all of these, briefly in the next few slides. So the first is what we call the opt package, and like I said before, the opt package is described on the lamps.sandia.gov website. So I put the link there. So basically, in the opt package, some people have taken C++ templates and rewritten the pair styles to reduce overhead. So to reduce the overhead of if tests and other conditional code. The code also vectorizes better than the regular CPU version. So this is CPU only, there's no GPU support, and the coverage is fairly sparse. It only includes 9 pair styles, but it includes a Leonard Jones. So that's an option if you're running on Leonard Jones on the CPU. So in order to use this opt package, you have to first compile LAMMPS with the opt package. So if I go to slide, it's very similar to this molecule package. You just say make yes opt or -D package opt equals yes. And then to run LAMMPS with this opt package, you need to use what's called a suffix command. So the suffix, this -SF opt, automatically appends an opt, a /opt suffix onto anything it can. So basically, for every pair style, for every other, like the time integrator or anything, it'll look and see if there's an opt version of this command, and we'll run it through the opt package if possible. And so in this way, all you have to do is just compile LAMMPS with the opt package, use the -SF opt suffix, and you don't have to change the input file at all, and you'll get speed up. And this is similar to all of the accelerator packages that I'll show in a moment. Okay, so the opt package is C++ templates to reduce overhead. Similarly, there's the user OMP package, which uses the OpenMP multi-threading on CPUs. And so, just a little note, LAMMPS uses MPI parallelization for this domain decomposition. This OpenMP threading is on top of MPI. Typically, using OpenMP, isn't faster than straight MPI and LAMMPS because there's some overheads to, for thread safety. The exception is when you're using a lot of cores, a really big simulation on a big supercomputer, you can get bottlenecks communicating through MPI. And so using OpenMP can help reduce these bottlenecks. But if you're running on a single node, don't be that surprised if OpenMP doesn't really help that much. One place where OpenMP can help is if you have HyperThreading enabled, and you can run OpenMP on the hyperthreads. And so to use the user OpenMP package, you compile LAMMPS with user OMP just like before, and then you use this -sf OMP suffix just like before, but you also need to set the number of OpenMP threads, and so you can do that through the OMP num threads environment variable. So if you want to run on 2 threads, then you'd set that to 2, and then just use the -sf OMP suffix. And then your simulation will run with MPI and OpenMP threading. Okay, so that was another CPU only package. The third and last CPU only package is called the user Intel package. So this is similar to the user OMP package, except that it's very specialized, and so it's the user Intel package basically will vectorize very well, especially on Intel CPUs. You can use it in conjunction with the user OMP package, and so if your pair style is supported, which it is for Leonard Jones and the Rhodopsin benchmark, typically if you're running on an Intel CPU, you absolutely want to use the user Intel package. It'll vectorize. It'll get better performance than, in general, than the user OMP package or the opt package. So in order to use the user Intel package, it's very similar. You compile with user Intel. You use the -sf Intel suffix, but you also need to set a few more options using what's called the package command. So this -pk is the package command in LAMMPS. I put a link for more information. And this basically, through the package command, can tailor different options for this specific user Intel package. So in the example I've written, I have this -pk Intel 0 OMP2 mode double. So what this is saying is that I don't have any offload. I'm using 2 OpenMP threads, and I'm using double precision for the calculations. Okay, so we talked about 3 different accelerator packages for CPUs. Now we're going to talk about the 2 accelerator packages for GPUs. The first is what we call the GPU package. And so the GPU package is designed for when you have 1 or more GPUs coupled to many CPU cores. The reason for that, or the reason that I say that, is that only the pair force computation runs on the GPU, as well as the Neighborless, some of the long-range electrostatics, and a few other things. Everything else runs on the CPU. So the time integrator, bonds, the molecular topology, any diagnostics, that's all on the CPU. And so in order for that to work, we have to move atom-based data, so the coordinates and the forces, back and forth between the GPU and the CPU every time step. If you can be linked, then maybe that's not so bad. So really, in order to parallelize the time integrator, the bonds, and anything else, you need to have multiple MPI ranks per GPU, so that doesn't become a bottleneck. One other option in the GPU package is that it will automatically try to overlap if you have pairwise on the GPU and KSpace on the CPU, it will automatically overlap that because there's no dependencies between those two computations, and so that can speed up your calculation as well. Okay, so in order to run the GPU package, it's a little bit more complicated because there's a GPU library found in the lib folder in LAMMPS. So that's one thing that has to be built. And then you install the GPU package, and then you compile LAMMPS. There's more information in the LAMMPS documentation about how to do this. But then once you have the GPU package built, it's fairly simple to run. You use the -sf GPU suffix, and then you can say how many GPUs are on a node using the package command, -pk GPU4 says that I have 4 GPUs per node and use all 4 GPUs. One thing I'll mention is that it's best to use the multiprocess service, CUDA MPS, when using multiple MPI ranks per GPU. This helps reduce some of the overhead. So you should enable that daemon if you can on your system. And like I said before, it'll automatically overlap pair style on the GPU with KSpace on the CPU. Okay, so that's the GPU package that uses CUDA or OpenCL. And like I said before, it only runs the pair style on the GPU. Most everything else runs on the host CPU. So the second accelerator package in LAMMPS is called the COCOS package. And so what is COCOS? Well, COCOS is an abstraction layer between the programmer and different platforms, different hardware. And with COCOS, you write your code once in C++, and then COCOS has different backends such as CUDA or HIP or OpenMP or SYCL, and it will map your C++ kernel, this small part of the loop, onto the backend language and run it on the different hardware. So like I said before, COCOS consists of 2 parts. The first is parallel dispatch, where you take your kernel and map it onto different backend languages. And the second are COCOS views. And these views are basically different ways to lay out your data. So a GPU may want a column major data layout, or like a Fortran or layout left is what we call it. Whereas a CPU may want a layout right, C-style data layout, or row major. And so through COCOS, you can switch between these different layouts at compile time. And so the LAMMPS COCOS package has taken this COCOS library and implemented it in LAMMPS. Supports both OpenMP and GPUs. And the difference between the COCOS package and the GPU package on GPUs is that the COCOS tries to run everything. So the pair style, any diagnostics, the time integrator, bonds, angles, everything it can, even packing, unpacking of communication buffers for MPI on the GPU. It tries to be GPU resident and keep the data on the GPU as long as possible. Only do transfer when absolutely necessary, like if you have to do some output or file I/O. There's many different options in the COCOS package, and so you can use the -pk COCOS command to toggle to set a full or a half we talked about before. So all these options are documented. They're all good things to tune for your simulation, depending on what hardware you're running on. Okay, so how do you run the COCOS package? Similar to before, one thing you need to specify is this -k on that says I want to use COCOS at runtime, and then tell it how many GPUs. So G4 says I want 4 GPUs per node. That's similar to the the GPU package that also used 4 GPUs per node in the previous example. And then you set the -sfkk, so that's the suffix command. So for example, if you want to run with for OpenMP threads, -k on T4, so T means threads, G means GPUs, -sfkk. Okay, and then one slide on how to overlap with COCOS. So like I said before, the GPU package, you can automatically overlap your KSpace on the host CPU and the peristyle on the GPU, so that can run asynchronously at the same time. You can do something similar with COCOS, but it requires a few more steps. So one easy option is to use the -pk COCOS pair only on option, and this will basically mimic the GPU package so that everything will run on the host CPU except the peristyle. And if you enable the KSpace, or if you're running the Rhodopsin benchmark, this will allow overlap. You may need to compile with this default stream per thread flag. And another option is you can set KK host or KK device suffixes manually in the input script. So this is a way. So if you set KK host suffix, that means it'll run on the CPU. KK device will run on the GPU, and so you can shift different computation from either the GPU or the CPU through these suffix commands. You can also compile with both CUDA and OpenMP backends, and then run with OpenMP threading on the CPU. So that would be a -k on, and then you specify both a T and a G. So 4 threads, 2 GPUs with a COCOS suffix. And again, there's more information in the lamps.sandia.gov website for the link that I posted. Okay, FFT libraries. So as I said before, the KSpace P3M method requires an FFT library. The default in LAMMPS is the KISS FFT, so it's bundled in LAMMPS. You don't have to do anything. It'll just run it. But other libraries, such as FFTW, MKL, or CUFT, could be faster. And so there's options to link with a different FFT library. And I would suggest, experimenting with these so that you can get the best performance. Because, like I said before, the default may not be the fastest. Okay, so one last thing to get the best performance out of your simulation is paying attention to processor and thread affinity. So this is basically determining how MPI tasks and threads are assigned to nodes and cores. So for example, in MPI run, you can use a bind to core or bind to socket. In OpenMP variables, you can use OMP proc bind and OMP places. And then you also need to pay attention to NUMA bindings. So for example, if you have a dual socket system with GPUs, then you need to make sure that the MPI tasks driving the GPU are on the same socket as the GPU to get the best performance. So these are, in the examples I just showed, very basic MPI run commands, but really you need to pay attention to the affinity as well to make sure that you have good affinity to get the best performance. Okay, so we've talked about LAMMPS. Well, we talked about molecular dynamics, what it is. We talked about LAMMPS, how to build, run, compile, the optional packages, the accelerator packages, how to run on the GPU and CPU. And now I'm just going to talk a little bit about the benchmarks that we're running as part of the tasks. So we have 2 benchmarks. First is the Leonard Jones. Leonard Jones is a very simple pairwise model. It's very similar to a van der Waals fluid. It captures realistic physics of liquid, vapor, solid, but it's basically a fictitious model. You could think of it as modeling a very similar noble gas such as argon. So it's basically, just spherical particles bouncing around in a box. Very simple. The second benchmark is the Rhodopsin solvated protein. So Rhodopsin is actually a protein found in our eyes. The model is the protein solvated in water, And as I said before, the Rhodopsin benchmark includes molecular topology, so bonds, angles. It uses long-range electrostatics to capture charges. You need to build with the 3 optional packages that I mentioned. And then I have 2 visualizations here. So you can see on the right, this is the protein surrounded by water. And then on the left, this is basically 4 replicas of this bilayer. And you can see, the different layers of the protein and the water. And so the image on the left was created through LAMMPS. You can actually dump out images in LAMMPS. I'll talk about about that in a minute. Okay, so you run LAMMPS. How do you know how fast it was? Well, in the log file, there's some timing information, and this is how we measure performance in LAMMPS. So the main way to measure performance is what's called the loop time. So this is the time inside that MD loop. So if you run for, say, 100 time steps, it's the time in that 100 time steps. It doesn't include setting up the problem or finalizing the problem. And so this loop time of 0.174.524, that's the number of seconds it took to run 32,000 atoms for 100 steps on 640 MPI ranks. And so you can calculate the performance of LAMMPS with this one line of output. Then there's also a timing breakdown, which basically says, where was that time spent? Was it spent in the force computation of the peristyle? Was it in the neighborless? Was it in MPI communication? Output like writing files, or in the other diagnostics or the time integrator? That's the modify command. And so you can look and see what's your bottleneck here, and then try to, if the bottleneck is the neighbor list, then maybe you can change some of the settings of the neighbor list. If the bottleneck is the force computation, maybe you can change, from a full neighbor list to a half neighbor list, or turn Newton flag on or off, or, if the bottleneck is the KSpace, then you can use a different FFT library, or, change the different KSpace settings or the cutoff, etc. One note is that on GPUs with the COCOS package, in order to get an accurate timing breakdown, you need to set the environment variable CUDA launch blocking equal 1. But you should only use this to get a timing breakdown, because it will slow down the simulation and prevent any overlap, any asynchronous calculations. So you don't want to use that to get the main timing, only to get the timing breakdown. Okay, so just a kind of a basic, what can I change in LAMMPS?
I have a question.
Sure.
How on the previous slide, the runtime is pretty short. So how do we make the problem bigger or make it run longer?
Yeah, so
we can just increase the number of iterations, but would it make sense, or is there another way to make it the problems as bigger?
Yeah, so in order to make it run longer, what you do is you change the number of time steps. So right now, we run a small problem on a large number of cores for a small number of time steps, and that's a very short runtime. You can change the number of MPI ranks. You cannot change the number of atoms for the benchmark. That's going to be fixed, but you can change the number of time steps. So you could run for 1,000 or 10,000 time steps to get 10 or 100x longer runtime.
Okay.
Yeah.
Thanks.
Okay, so what can I not change? So there's a full list here on the website that I've listed below, but basically you can change anything that, you can't change anything that changes the simulation results. So that would be the number of atoms, time step, turning off or changing the model, anything about the model or, significantly change the result, you cannot change. You can change anything that makes the simulation go faster that doesn't change the model. So that would be, changing the Neighborless, the Newton flag. There's a full list here of what you can and cannot change. And if you have any questions, just talk to us and we can clarify too. Okay, and then as part of the task is to visualize the simulation. And so in both of the benchmarks, there's a LAMMPS dump image command. So it's commented out because it will slow down the simulation. So you don't want to use that for your timings, but to make a PNG image, you have to link to a PNG library when you build LAMMPS, but then it will automatically dump out the images that I showed. If I go back here, this on the image on the left was the dump image command. You can, there's different settings. You can zoom in, you can make different colors or, do different settings there. There's other options as well if you want to use a third-party library. So there's the Visual Molecular Dynamics, or VMD, that you can download for free. And then if you have a LAMMPS dump file, which there's also options to uncomment in the benchmarks, you dump out that. And then with VMD, you can have a GUI, run that on your computer, and you can, rotate and look in and zoom in. It's interactive. The LAMMPS dump image is just one snapshot. You have to set the settings in the input file, and you just get, one snapshot of a fixed camera view. With VMD, you can rotate around and look at the simulation cell. And then same with Oviedo. Oviedo is another third-party library or program that you can use, similar to VMD. Both VMD and Oviedo are specialized for molecular dynamics. VMD is more related to, say, proteins and biological systems, whereas Oviedo is more related to material science, so metals and polymers and things like that. And finally, how do you get help? If you have a LAMMPS question, if you're having trouble running LAMMPS, the best resource is to look at the LAMMPS documentation. So it's bundled with LAMMPS as well as online. There's also a LAMMPS mail list. So if you have questions, you can post a question. Well, you don't even have to, post a question. You can just go search. If you have a question, you can go search the archives. If you can't find the answer, you can post a question. But there are, some guidelines about posting on the mail list. So, read those guidelines first. But, feel free, there's lots of beginners on the mail list, and we try to answer the questions and get people the help that they need. That's all I have. So are there any other questions?
Can you hear me?
Yeah.
Okay, so I have just a little questions about the minus PK and minus SF option. So
Okay.
are they mandatory or not? I mean, if I don't use these options, if I compile with, say, the Intel module options, and I don't use anything, do I have the behavior that I think I will have, or I mean, this option are just to modify the way the Intel package works, or because if I just compile the program with Intel package, sorry, so I will have an Intel optimization, I would say. So do I need to use the minus PK option, or should I just not use it and I would have the default Intel behavior?
Okay, so even if you compile with the user Intel package, LAMMPS won't use that code unless you use this minus SF Intel. And then you also need to set, well, the default settings for the package might be okay. I can't remember what the defaults are, but but LAMMPS will not use the optimized code unless you use this suffix command.
Okay, so thank you. So that was my question. And just another question, but it's more at the beginning of your how do you track when an atom change of domain in the decomposition? Because it can arise that with the different moves of the atoms, then an atom that was in the first domain will change to another domain, so it will be held by another CPU or something like that. So how would you track that?
Yeah, so we have what's called, so when the Neighborless is rebuilt every, say, 10 to 20 steps, there's different communication parts, and one of the part in LAMMPS is called what's called the exchange communication. And so the exchange communication is taking an atom from one subdomain that's owned by one MPI rank and handing it over, exchanging it to the other MPI rank because it's migrated out of the boundary. So if in between reneighborings, it will just be in this ghost region, this extra halo exchange region. So for 10 times it'll just be a ghost atom, but then when we do the reneighbor, then we shuffle all the atoms around and the owning processor is changed during the reneighbor. Does that make sense?
Yes. Okay. So, because we have the same program with Thinker HP, which is the program that I wrote, and so I just want to know how we can. So you have just a specific exchange communication for this kind of problem. So you just exchange the position with atom that comes from one domain to another.
Yeah, so we just do a point-to-point nearest neighbor MPI communication, take that atom data structure and move it to the other proc.
Okay, thank you.
Any other questions?
Hi, Sophia. I would like to add a few more things towards our time. One is that we are going to test it on. You're going to test it on 2 different clusters. I mean, you have the resources. One is the Niagara cluster and University of Toronto, and the other one is the Singapore cluster, NSCC. And the Singapore clusters has also a DGX cluster, so you can use the GPUs over there. The Niagara cluster doesn't have GPUs, but it's slightly newer on the CPUs. It uses Skylake CPUs. So those are the resources we have. Those 2 clusters, each one is using different scheduler. So if it's your first time using those clusters, the Niagara cluster uses SLARM, while the NSCC uses PBS. It's just a matter how you schedule your job and run it on the nodes. I might do another session. I'll try to see if we can. We try to push another session around how to get started on the cluster. We wrote few getting started guides, but sometimes those things slightly hard for people that are not used to those schedulers. This is before even to be able to run the application, you need to schedule it on the cluster. And the input files for the LAMMPS, we'll try to publish them this week. And the cluster access, I'm targeting next week, so you can get those. The IT guys on the cluster, the managers, are working to supply you the access. So once we get it, I will send it to you. If any more questions, just feel free, or if you can, after that, even if you have later questions, you can put it on the Slack channel or contact us, whatever is easy. Okay, so if no more questions, I would like to thank Stan And the rest of the people that joined us to hear that was very, very nice and enhancing. I'm sure that some questions will pop up as you start testing, and feel free to contact us, contact Sam, contact me. We'll try to help you as much as we can. Okay, I will upload the recording and the presentation slides to the website, and I will send you the links. And thank you, Stan, and thank you all for joining.
Yep, thank you.
Yes, thank you.